last time I hurriedly show a graph in which delta n going to PN over NPO, it should be actually shown to 0. Delta excess carriers will decay and they will go to their equilibrium value of whatever NP0 or PN0, which is whole concentration in N type in equilibrium or electron concentration in P type at equilibrium. Our symbolization. Is that clear? So having told this, one interesting feature about this, you must also look into the fact that if there are excess carriers, which is say new carriers n is equal to n0 plus delta n and p is equal to p0 plus delta n or delta p, then obviously for the time these carriers are present, even if they are time dependent, there is an excess carrier. So what is going to change? The conductivity of any material is decided by Q mu Pp, and if this is going to change, this shining of light of different intensity will create more delta n's or delta p's, and since they increase the n or p value, obviously the conductivity will change. Is that correct? So if initially you have a semiconductor material and you know its conductivity or equivalent resistance of the power if you have, and then you shine light, even momentarily larger than tau of course. So it will create whole electron pairs, and then as soon as these carriers will create, sigma will boost immediately. So if you have a circuit which has this bar of semiconductor which we call photoconductor, and there is some circuit which requires triggers when the current conductivity goes down or resistance goes down, so I can create a pulse at the output. Initially resistance is high, and as soon as the resistance reduces, there is a pulse at the output which may trigger some circuit. Is that correct? So this is an interesting sensor cum actuator. What is the difference between the two words I said? A sensor senses that yes, conductivity has changed. Actuator means which actually actuates something else. So switch on off is essentially actuator. On off switch is actuating something, starting something. So a photoconductor can be used as an actuator because it can work as a great photosensor. So most of the photosensors which you see as a diode sometimes essentially changes its conductivity, and so which will be very good which has a larger change in conductivity from its original value. Larger the shift, better pulses will be observed, good switching can occur, and so you must search for materials which absorbs more light, which actually changes much more conductivity. Okay. These are essentially one of the major devices which you use in many optically switched circuits. Okay. Nowadays we are looking for optical switching. Why I said first few days I said that we are now trying to see, can we do a transmission of signals optically without going to electronics. Okay. So I want full optical system. But I figured out, even if I try that, I will require semiconductor to do this because it's much easier to create optical signals or modulate them in semiconductors. So one of the property which I'll use there is change there. Okay. So change in intensity will also change the carriers. So there is something which we are now looking as optical systems, and there such devices may find its first use. There is a chip available now which has optical interconnects. So everything else is silicon, is normal electronics, but the signal from one point to other actually moves optically. So then you require conversion of electronic signal into a light ray signal which will transmit on either in the air or in fiber if you have fiber connections inside, and if that's so, it will be picked up by a photodiode and it will come back to electrical signal. So there are methods now people are looking. So optical actuated systems are becoming very dominant in 2000 ahead of them. Earlier we were only electronics, so it's okay. Now we are looking for, why we are looking for optical? Very high speeds compared to any electronics in solids. The speeds will be, free space is so much, 20 or so many. So it's fantastic to use optical signals. However, what will be the problem? Optics has its own problems, lot of scatterings, lot of diffractions, lot of interference. So all those issues will also to be addressed. That's why we do put fiber, because it actually restricts everything. But if you want free air transmissions, which probably one is looking now, that I can do a satellite transmission through lasers. Okay. So that's what a new thinking is, that why not use full laser beams? But then you need huge power to beam that. How to create concentrated, say, megawatts of laser is no one thought so far, even pulse laser. So that, why I showed you all this, because you must remember that there is an interest going on in these kind of devices, that too. And other, of course, the major use which we'll see later is the photodiode, is the solar cell. Because now one is finding that the energy is going to create the ultimate limits for any nation to progress or any society to progress. And the rate with which we are consuming energy is too much to, this experiment may increase further. So how to generate power? One, of course, is fossil material fuels, which will not last more than, maybe of course your lifetime, you don't worry, but next generations. So one is looking for sun energy and therefore related to solar, and believes that sun has still lifetime some million trillion years, so maybe earth, I don't know. So in that case, that energy is harnessed. So once you get into optics and you want to use multiple devices on that, one of this device will be based on semiconductors, and this is what we call photovoltaics. Okay. So there is a lot of research, people may not be aware. IIT Bombay has an energy center department now, and there used to be center earlier, it's now become independent. So that department has a project, last year learned from Professor Vasi course, I don't know, he must have to, he's the chief of that center, photovoltaics. So we are, of course, there we are not just looking semiconductor, we are looking dye based and variety of other chemicals we are looking into. But the idea is to look light, is that clear? So first step will be somehow conversion of one energy to the other. This is therefore called converter of energies. From light, okay, electrical, from electrical by photodiode you can go to light, LEDs you can go back to light. So this is the photodiode LED system which can do conversions. Therefore study of this has some relevance. आजकल क्या है, सबको बताना पड़ता है, ये relevant है relevant. Okay, so what is this conductivity will be called? It's called photoconductivity. Change in conductivity from higher to lower is essentially due to photons, therefore it's called photoconductivity. So there is a huge effort was made to find different kinds of photoconductors, and in 98 someone won the Nobel Prize. Anyone? ढूंढ के बताओ कल गूगल पे कौन था? एक एशियन था जिसको ये अवार्ड दिया गया था, नोबेल प्राइज. पर ऑफ कोर्स इट वाज नॉट सिलिकॉन, इट वाज ए ऑर्गेनिक सेमीकंडक्टर, organic semiconductor photodiodes or photoconductivity was measured first time, which gives relatively larger conductivity change, and he won the Nobel Prize. So silicon is not the end in itself, but silicon is very starting material, because most of the electronics is known, most of the electronic systems are known, so we want to utilize whatever we have done in the last 50 years. We keep using electronics everywhere, so ultimately we may have to probably change. That area where we actually will work both electronics and photonics is called photonics. So the new area of research in communication and microelectronics or nanoelectronics is called photonics. So new area of research now in most of the universities in the world is on photonics. So this is some kind of basic thinking which is going on using photonics. Okay, so let's look further. Since initially the system is in equilibrium and has some electron and hole concentration of N0, P0, obviously this concentration when I shine light will change, that's what we have seen. So we will like to say, okay, if additional electrons are coming, additional holes are coming, so recombination will start because equilibrium has to be attained, and this equilibrium we call not thermal but called steady state. Something is generated, something is recombining to return back to, so system will remain time invariant after a while. This system is we call as steady state. So if we have attained the steady state, then When we wrote the Boltzmann relation, what is the criteria we wrote? N is equal to Ni e to the power Ef minus Ei by Kt. So we wrote this relation. When we say it is in thermal equilibrium, this Boltzmann relation was written. Similarly for P we can write. So what they say? The system is in thermal equilibrium. But now you are disturbed thermal equilibrium. You are in non-equilibrium situation. However, the difference still is that time invariance is still possible, and therefore system is in steady state. So we said, even if it is not correct to use this Fermi level theory in non-equilibrium situation, at least in steady state, we can still use this expression, and the Fermi levels now we will call them as quasi, because they are not the real Fermi levels. So we introduced a concept which we call quasi Fermi level. So if I have to write N, which is the new this, I can still write this. I will say EFN minus EI by KT, and for the holes I will write exponential minus EFP minus EI by KT. So what is EFP and EFN says? It evaluates the number of extra electrons which you have generated now, additional electrons you have generated. Because of that the net concentration has changed. So the Boltzmann relation we want to keep using it. But we know very well that Boltzmann relations are only valid based on thermal equilibrium. That's how statistics were derived. However, there is no equilibrium attained. But pseudo-equilibrium is possible. So we say, okay, pseudo level will assume, and we call them, so this EFN and EFP is called quasi-Fermi levels. This is very important method because this allows us to do something interesting. EFN and EFP essentially, because you can see from here, let's say you have an P-type material, this is your EI, EC, this is your P-type material, okay, slightly here, initial EF, okay, and when you shine light, there is extra electrons and extra holes, so there is a equivalently saying, there is a EFN and there is a EFP which is created because additional holes and electrons have appeared. Because of that, Fermi level as if split. Yes. So that is why I am trying to say that if we are not saying that it is statistics being followed now, because that's what we said why we said quasi, it will still give me an idea how many carriers I have in the system. And this separation of Fermi levels is essentially a measure of the energy it received or stimulus I have received. So indirectly I am now saying that change in this has occurred because something I applied. Okay. So energy levels, officially there is no Fermi level which you can really show for the nonlinear system, non-equilibrium system. But we now say, okay, number wise at least I can know because I know how many electrons I have. Equivalently say EFN is above En, so this many electrons, EFP is away from so much, so many holes. So this only represents the number, it doesn't say physics on it. This is therefore called quasi-Fermi levels. However, the splitting of Fermi levels essentially is the measure of change due to non-equilibrium situation. Is that correct? Otherwise there would have been a fixed EF everywhere. The split which we showed just to represent the numbers is called quasi-Fermi level. Quasi is that word clear? It's not real Fermi level. Even the Fermi level itself is a fictitious level. Okay. This is fictitious, square of that. Okay. But essentially it gives me numbers. Okay. So I know how many electrons and how many. So measure I have immediately. And this has changed because of I applied externally something. Is that correct? Optical or electrical, any of the four which I said can happen, and I may say change. As soon as I see change, I say, okay, why don't you use this? And many a times people don't just write this, people may write this. Of course, all sign, of course holes have plus Q, so it will remain like this. What is this called? Quasi-Fermi potential. It's called quasi-Fermi potential. Phi P and Phi N are called quasi-Fermi potentials. Is that clear? Similarly, many books write EI by Q minus for this as psi, or some only write what I don't know what is how it, bigger phi, how do I show here? Straight one sign. Either they write psi or they write big phi. Okay, as potential related to what? The intrinsic Fermi level E by Q, EI by Q. So why I am showing you this symbolization, because in PN junctions I will probably go to these symbols, because in PN junctions this will be required. Is it true? Because there the concentration is going to change, that's what junction is going to do. So we will represent how many carriers either side we are receiving compared to before we applied the voltage. Is that clear? So to do this is one way of representing numbers. Please remember, Fermi level itself was a concept. There is no such, because in a forbidden gap or a band gap there is no level. So Fermi level itself is a measure of some carriers. So we say, okay, in additional carriers come, we may still use this if the system is in steady state. If they are constantly changing, then even this may not be very true situation. So the presence of the representation by Fermi levels, quasi-Fermi levels, helps us to evaluate the numbers quickly when the stimulus is applied. Is that clear? This is very interesting, because this is where we will actually figure out later the difference between, or let's say if I multiply this. If I multiply this N and P, what I am going to get? Okay, should I, or maybe I'll rub this. If I multiply N and P, I am going to get exponential, yes? This EI will cancel, and EFN minus EFP by K. If I multiply NP, then I get Ni square times exponential. So in a normal equilibrium, Fermi level is same, one common Fermi level. So what does that mean? EFN is equal to EFP. Then what is the formula I derived? Law of mass action? NP is Ni square. But if I disturb the equilibrium, NP is not Ni square, but Ni square into exponential difference between the quasi-Fermi levels. Is that clear? So this now tells me that if I change the equilibrium, how many additional carriers I am going to get, which will be proportional to EFN minus EFP. So this concept was thought because anyway I am going to apply voltage and I want to see change. Okay. And if I know the change, what can I calculate? All currents, because I know dN by dx or dP by dx, I know the fields. So I can calculate drift currents and diffusion currents. So at the end of the day I am looking for currents. Please remember, all the theory which we do is to finally get what relationship? IV and CV. Our ultimate aim for a device is to get an equivalence of a diode or any device in terms of some kind of RC or whatever, maybe this also, I don't know what model we will get finally. Some kind of a model I am trying to seek equivalence of that. Where R and C may not be a constant value, they may be functions of applied bias or applied anything, and still I can be able to evaluate the output response of such a device. This is what ultimately I am looking for. I am looking for electronic system, so I am looking for response. But to do this, I must get equivalence. Okay, these are called equivalent circuits. So for every device, we must be representing it into an equivalent circuit. And then we can put into a normal network, replace that device by this, solve network. So much networking we do. We know kashyap law very well, hopefully so. Okay. And therefore we can always solve a network using kashyap laws. Okay. What is Telegrams theorem? चल पूछ, नेक्स्ट टाइम पूछूंगा मैं, एक कोई तो भी पढ़ के आओ. मैंने कहा you have finished network course, so you have to. Okay, then I should not say. Okay, you learn this is very interesting, something related to power. Okay. So please remember that at no time device people should forget. The problem with most of the device people like us, we tend to believe that our interest is really statistics, how many carriers, why they are there, and ends there. Okay. So that enthuses you too much. Whereas in real life, I don't care whether electrons move, current kitna. So essentially as a circuit person, electrical, we may not know what device is, as long as you can represent the device in terms of its equivalent circuit, and once I get that, I say thank you very much. Okay. So our course at the end must lead to that okay, here are equivalents for all devices which we discussed, and now in future do analog or digital or whichever course you do, just represent that device by this equivalent and so on. Is that correct? There will be a current sources you may get, so voltage dependent current source, current dependent voltage source, current dependent, all four possibilities can be done, and then you can solve the network very easily. Is that clear? So this is the way devices people look, that, but for us to reach that equivalent must be closer to the reality, is that we measure something, we know this is happening. Now I am coming back in device, if my equivalent circuit does not give the value which I get in actual measurement, my model is not correct. Therefore I go back and keep fishing out, what could I have added or subtracted out of this model of physics now, which will probably commensurate to what I really see in my life. So that is why the modeling word starts. So what is the easiest way of modeling? Put an equivalent model for that and start tweaking the value using some, like I represent some function as a plus b e to the power c by d x. Now start putting a, b, c, d, e, f, constants keep varying, some function will always get fit. This is called fitting function. So I see an IV characteristic, it doesn't follow my physics, so I said okay, ये formula पे इसमें fit है. So I say okay, this is what device is about. Okay, this is the function. Now I don't know why A is 2.7 or B, because some combination, other combination may also fit. So then I say no, this is not correct. I know physically something happens like this. So formula should be similar like formula everything. But the constants, fitting constant I will add to that so that it actually fits the data I observe. This is essentially all modeling people do. They just trick around those constants and still think that physics is not violated. Actually physics is 100% violated when you are putting A, B, C, I'll attach with that, okay. But we still believe, I have kept mobility term, so what there if I say C mobility, or C times something. Now C I can vary from 10 to the power 1 to 10 to the power 18. Then you are not using mobility of 1300, you are using any random number. But the way modeling people do is to actually get the data and put it on a real physics-like equations, so that for our satisfaction होता है कि हमने physics violate नहीं किया है. But essentially this is how you fit. But you take any polynomial in a third order, any conic section can be fitted. Any conic section. It may require polynomial of the 99th order. ठीक है, हम वहाँ तक जाएंगे, but fit तो हो जाएगा. So the idea of fit functions are that it can represent anything. But since, as I say, as a natural human being, we go, this is too bad. This is only maths, so we should go to maths department. So we don't like it. So we want to keep our understanding and pick on that. That's how all fit models are created. So when you actually solve circuits in computers, which is called SPICE or something we do, then you'll find that the model card you can even replace yourself. So they have built in one, but you can also put your own models there. This idea was created out of this. Okay, this is something additional I thought you should know. So this is roughly what excess carrier word was looked into. Now we stand little ahead, because we are still not evaluated the net currents available to us. That is, that net current of electrons must be two parts. One is due to drift, the other due to diffusion. But we are independently seeing drift, independently seeing diffusion. Now we want to say together what happens if I have a semiconductor, some electrons are going in, at some point what is the number now with them if there is a gradient. The diffusion occurs because of gradient. We will like to see under gradient how this happens. Is that drift field still there? Yes, because drift will not allow infinite diffusions. Okay. So there will be a built-in fields also there. Once the field term comes, what is the current will be available? The drift current will be available. So we will like to see overall how much is the electron current, how much is the hole current, and then how much is the total current. J is equal to Gn plus J. This is the next thing I want to do. So I need another equation to do this, and that's a very interesting equation. I think the equation which I am going to solve now or derive for you, which is simple, is used not only in electrical, it's used in every kind of transport. Every kind means even fluid transport, chemical engineers use that, thermal people use it because heat energy flows. So anything related to energy transport, this equation is a must and must be solved by everyone. This equation is popularly known as continuity equation. Obviously continuity equation has something to do with time dependent, because continuity can only occur if there is something change happening. Is that clear? So we say we have a system in equilibrium initially, we apply some bias which we say, which may be electrical bias or it may be any other bias, and it changes system to non-equilibrium. However, there are forces which ties that back to equilibrium side and therefore creates steady state. So under steady state, this equation is valid. Okay. So here is a figure which is given in different shapes. This is my figure. Some other book may have some other shape shown, but doesn't matter. It is same. One cannot do much different from what I am doing anyway. Here is a bar of semiconductors. Okay. Let's say this direction is X, transport is along this direction. Okay, maybe. And there is a plus V volt I apply, so the electric field is in this direction. I mean, just to show you voltage, because otherwise you say from where X, so I actually applied voltage. Now I say at any point X here, say this is 0, let's say, from here. So at any point X, I have an element which is thickness of this is dx. A small infinitesimal small element at x with a value of gx as its thickness. Let us say we are looking for electron transport. Okay. So at x is equal to, at this point, the electron current which is entering this element is Jnx. What is current density in terms of flux? What is flux? Number per unit area per unit time. What is current density? Charge per unit area per unit time. Net charge. Qn is a net charge. Charge per unit area per unit time. So flux, and this is no different except that Q is additionally put there. Let us say this area is A. So I will say cross-sectional area of the transport is A. In real life, this shape may not be constant A or something, but derivation could be, we can somehow, by area we are anyway going to do, so whatever area you get, you don't worry right now. But to get it simple, we first start looking into constant areas. So okay, this is J and X entering at this point. At x plus dx, this is entering at x. Maybe I will remove this area term which you might have written by now, just to give this, I may just write this as an area A. Then at x is equal to dx, x plus dx is coming out of the entering at x in the box. Coming out of box, Jnx is entering and Jnx plus dx is coming out. The reason why it is happening, because we say there is a gradient. Under this case, what we have is not uniform concentration, it is a gradient. So some flux is entering, some flux is leaving this box. Now there can be many possibilities, but think about this. We figure out that Jnx plus dx is larger than Jnx. Let's say. That is, the flux coming out is larger than which is entering. So what could be the causes of that? So as soon as Jnx means number of electrons right now, per unit area, per unit time, but this number which is entering here, this electron concentration inside the box may increase. If Jnx plus dx is going to be larger, the electron concentration in the box must increase. So how it can increase? By a generation recombination term which will be present everywhere, so is in the box, the additional electrons may be generated in the box, some may be combined by the time they travel, okay. So there is an additional electron concentration which may come out of the box, is that correct? There will be four possibilities I am going. First, four points I am saying. One, electron entering, one additional number may come from the generation, some may be lost in the recombination, and the rest will come out of this. So what will be change, you can see, Jnx plus dx minus Jnx is the change of electron related flux coming out, and that may have additional two terms, generation minus recombination. So then only then some kind of steady state can be achieved. Now this essentially says that whatever is coming from here can get modified under gradient issue. However, this must be continuous, because now I am constantly applying bias, so there is a constant flow is going on, and this relationship is always maintained. This is called continuity. There is a continuity of carrier transport along the gradients, and therefore it is called continuity equation. We want to derive that. So let's not, having said, I repeat, there are four things are happening. Some flux of electron is entering, additional number is generated, is adding, some number is lost due to recombination, and the rest, therefore the out is coming is Jn plus x. So these are four separate parts we are looking into, and therefore based on this, okay, if I say I want to know actual number, not density, okay, n is the concentration. Let's say n is the concentration here we are worried about in the box which is changing. So how do I write the number change, that is number per unit time? So we say dN by dt is the volume change per cc hai. So if I multiply it by volume there, then I get the number per second. So I say okay, the rate change, actually it can be partial, but I am not changing partial, into A dx is the number of electrons. Now it is volume has been cancelled, per cc into A dx is cc, so that cancels. So number per unit time which is changing in the box. Okay. Now this we can now correlate, okay. We can see from here this number change from that value we see. Please remember I am not putting q here, so it is the number I am looking. So the first thing I should do, I put something here which will divide by q, because I am looking for numbers, not charge as such. So I say whatever is entering here, Jn x plus into what? Into what? Area. J is per unit area. Q I divided, so it is number per time. So this what you thought the left side must be equal to the right side. If you know very well, this is essentially can be expanded in Taylor series. How? Jn this is directly I can write, but those who feel that maths could be also shown, it is djn by dx partial into dx and so on. This is Taylor series expansion. If I substitute and let's say higher order dx squares are smaller, only these two terms I substitute here. So what do I get here out of this? dj by dx. Is that correct? dj by dx. What is the other method? This is very simple. You can see fx plus h or dx minus fx by x when limit of x tends to 0 is essentially df by dx. So whichever way you look at it, this is essentially same. That's what maths is trying to tell you. So if I write this expression, I like series expansions very well because series tells us that some approximations are being done by us. Like limit of x tends to 0 is an approximation going on. So we keep saying that Taylor series does allow us to see how many real terms I am giving. Okay. That's why many times people believe that we should not just use the standard formula, but write series functions and then say, okay, I neglect this because of something. That gives you a little more physics in mind that what we are actually doing. So it's not that most books will tell you like this. I just showed you the other way because how I should look into it. Okay, so if I write this expression here and area cancels everywhere, or maybe I can first rewrite. As I said, okay, maybe as book alright, it's a partial derivative because it's time dependent for a while. So a dx is equal to minus 1 upon q, minus it will be plus, okay, this minus djn by dx, so plus it will become dx, okay, into area into dx. So this cancels, so I get dn by dt is equal to 1 upon q djn by dx. Oh sorry, I'm sorry. Okay, actually this itself has a minus, so this will become plus. Electrons. In the case of holes, that sign will be positive, so final sign will be minus. In the case of electrons, Q is minus, so minus and minus it will become plus. Is that point clear what I said? Here I should put minus because I am talking of electron currents. If it is a hole current, I will put plus there. So therefore this sign will come plus for electron. You have done this in last time, this sign will come plus. Now, if you say, in this doing all this, we only looked into flux entering and flux leaving, but we did not bother very much. Inside the box there are two more mechanisms which was changing the concentration. That's why I say 4 numbers. So in real life, I must add G minus a generation term and recombination term. So the flux entering will give you a gradient of dj by dx plus additional generation, that is what the gradient and recombination term is giving. So dj by dx plus generating term. In most devices this G may be 0. There is no light, there is no additional process, so I can say G may be equal to 0. But as a general base, I may say generation term minus recombination terms. If there is an additional generation term you put there, otherwise you need not worry of this very much. But how much is R can be? Recombination rate is proportional to what? We just derived few minutes ago. Delta n by tau, delta n by tau. So if it is n minus np0 or whatever carriers we say, if it is a p-type semiconductor and we are looking at electron transport, then np minus np0 by tau n0 is essentially r. So we know r. Now we know dj by dx as the term, and this. In the case of steady state, which term I should make it to 0? dn by dt. Because in steady state, what is the criteria we declare steady state? It is time invariant. It's universally now looked as if it is constant. Though two processes are time dependent. Something in and something out is a time dependent, but as a system it looks as if it is time invariant. And therefore, if I want to solve this equation in the steady state, then in steady state dn by dt is 0 is equal to 1 upon q djn by dx plus generation minus recombination. If it is the other kind, similar relation can be derived. dp by dt will be 0 minus 1 upon q djp by dx plus g, maybe gnrn dp minus rp. Similar expressions can be derived for p transport. What is the diffusion term under gradient? What is the diffusion currents we have talked about earlier? What is the diffusion current in gradient? Jn diffusion, let's say, how much is? We have derived, no? What is the expression for that? Q dn by dx. If there is a gradient, q dn by dx. So djn diffusion by dx, okay, is q dn. Now there is an assumption we are doing, that the diffusion constant is constant. Otherwise, with respect, in fact that may not happen. As I say, mu is a function of nx, okay. If n changes, mu also can, of course the number has to be large enough, but otherwise mu is a function of n. N is varying, so is mu is varying, so is d is also varying, okay. But first order, we say dn is constant. So if that's so, I have already d2n by dx square, okay, as the djn. Then what do? I substitute that current, substitute that gradient dj by dx into this continuity equation. Is that correct? I have derived the djn by dx. So I substitute, same thing I will not do for p, which is identical to that. So you may, finally we may write directly on the p. So if I substitute this, then I get 0 is equal to q cancels, so dn d2n by dx square plus g minus r for n. Okay, this can be further written as dn d2n by dx square minus n minus n0 divided by tau n o plus g is 0. Same expression I do. So this flux is coming because of the gradient. That's how we started with. There will be a built-in field which will evaluate and must be compensated. So when I calculate the net current, I will use the drift component. Is that clear? I am not saying there is no, right now this flux is entering because of the gradient. Is that correct? So I am looking first that diffusion current which is because of the gradient. Then I will add what is the additional field component it is going to add. So as a total Jn must be having diffusion current plus drift current. Okay, so this equation which we wrote, and as I say in most cases, this term we can neglect because internal to this, that generation term may not be, there is no additional term which can, it's a thermal, but that anyways will go also with R. So we can say change essentially does not require G every time, but if there is an optical or something you are doing, this term will start also appearing everywhere. Okay. Can you see this equation is second order differential equation which can be solved. So what do I get from this equation if I solve? Nx. I get the profile Nx. But I also see this term is actually going to multiply this. When I equate it, it will get multiplied. Okay. So which term I am going to get? dn into tau n. What is the unit of d? Centimeter square per second. Time is, tau is in time. So what is the unit of this? Centimeter square. Centimeter square. So if I do this, it has a unit of length, which means dn tau n, which is a product, essentially under root of that, has a unit of length. What does that signify? What is d? Is a diffusivity, diffusion constant. What is tau? Recombination term. So d tau is the length, under root d tau is the length, characteristic length, which say up to which diffusion and recombination will come to equilibrium now. This is called diffusion length. This is called up to which diffusion will start actually effect enough that recombination it can start helping to bring the system into equilibrium. So d tau under root is called characteristic length, which is called diffusion length, okay, which is very important for in all calculations. This L is called Ln, is called diffusion length. So please remember d tau has length square, so under root d tau is lengths, and these lengths are called diffusion length. So now you can think of it. Yes. What I am saying, if I solve this equation, I bring that other and then I multiply by, so I get a term d tau, okay. Under root of d tau has a unit of length, so we say this I define as the term called diffusion length. Physically I then see there are two phenomena that I am seeing. One is recombination, one is diffusion because of the gradient. So I say if I had to bring system into steady state, that means by the time it will take some length, by the time this will actually come to steady state. So it is a measure of your diffusion as well as recombination which is bringing system to steady state. That is the length up to which these effects are dominant. Then it will become steady state. So dn by dt will continue to happen as long as the trial is up to this. Once this reaches this length, you say it will balance it out. So that's it. So therefore it is characteristics. Okay. So okay, now 4 equations therefore we can write. Similarly, we can write for holes in electrons. So here are certain, one more equation which is very important there. Okay, इस equation का नाम आपको आना ही चाहिए. D by E, sorry, I should write D by dx. What is this equation called? Very famous equation. Poisson's equation. Where is the charge density? Okay, so it can be, in the case of semiconductor, one can write something like this. Charge density is net charge into Q. Okay, Nd plus Na minus P minus N is the net charge. Now some numbers will be larger, some may be neglected, that's fine, but this is net. Epsilon is dielectric permittivity or Ks into epsilon 0. This is K of the material, let's say in case of silicon, into this is dielectric constant of silicon in our case, okay, multiplied by free space permittivity is epsilon of semiconductor. However, we know electric field is the gradient of voltage. That's what we all the time say, na? Integral E dx is the voltage minus sign. Okay. So once I know this, I can modify this d by d terms. I put a minus d2v by, d2v by dx square is equal to rho by epsilon. So I now start looking into voltage term because I am interested in what? Current voltage relationship. So I see, okay, in a semiconductor, from the charge density, I will look into voltage term. Is that correct? The current terms I will get from the Jn diffusion, Jn drift, Jp diffusion, Jp drift. So now I have current related to epsilon, electric field is related to voltage, which is related to charge density, and therefore now I start looking that I can create a relationship between ions. Is that clear? That's ultimately I am looking how current gets related to voltage. So I added another equation which is called Poisson's equation, which relates the voltage term with the charge term. Once I do this, I have so many equations I write, 6 equations I will give, one of them is this, and any of these current equations will be valid, not necessarily all at a time, because sometimes diffusion may not be strong, sometimes but they can be always represent together, all of them. Some may be negligible, some may be larger, but the terms are always present. Okay. Number wise you may neglect few of them. Is that clear? So we will next time write down full equations which all semiconductor theory will require, all of them. These equations are sufficient to solve any of the semiconductor device problems. We will list them out and we will show you that once you know this, take a PN junction at the first device and see how you apply them to get exactly what we are doing. Is that clear? So next time